everyone, today we're doing notes for 8.4 compound interest. So compound interest, this is the interest computed on the original principal as well as on any accumulated interest. The compounding period, this is the period of time between two interest payments. So as a reminder, our simple interest formula is A is equal to P times 1 plus R times T. So number 1 here says, assume you put $1,000 into an account that makes 10% interest. If the interest is compounded annually, we have to find out these few things: the first year, second year, third year, and then after T years. So we're going to use our simple interest formula because our interest is compounded annually here. So our P is 1,000. Our R is going to be 0.1. So after the first year, A equals 1,000 times 1 plus 0.1 times 1, which gives us $1,100. Then it says how much is in the account after the second year. So for the second year, we have A is equal to, now we're going to use this amount, our 1,100. That's our new principal, times our 1 plus 0.1 times 1, which gives us $1,210. How much is in the account after the third year? All right, A equals, now this time we're looking at our 1,210 as our P, times 1 plus 0.1 times 1. This gives us $1,331. So it says how much is in the account after T years. What happens here, if you notice, this amount gives us our $1,100. So here I can rewrite this formula. A equals 1,000 using part A times 1 plus 0.1 times 1 times that again, 1 plus 0.1 times 1. If I put all this together, that gives us our 1,210. So I could rewrite our formula for C as 1,000 times 1 plus 0.1. I'm not going to write the times 1 because it's taking up a lot of space, but we know this is now repeated 3 times, etc. So if we want to know how much is in the account after T years, if you notice, we can use our 1,000, that's our principal amount, 1 plus 0.1, and here for 2 years it was repeated twice, the 1 plus 0.1. For 3 years it was repeated 3 times, so we can use that as our exponent, 1 plus 0.1 raised to the T power if we want it for T years. So calculating the amount in an account for interest compounded annually, this is our formula. A is equal to P times 1 plus R raised to the T power. P is the principal, A is the amount in the account T years later, also called the future value. R is the annual interest rate expressed as a decimal, and T is the number of years. So it says assume you put 1,000 into an account that earns 8.7% interest. If the interest is compounded annually, we have to answer a few questions. So for this first one, P is 1,000, and now we're earning 8.7% interest. So R is 0.087. Future value in 20 years. So we have A is equal to 1,000 times 1 plus 0.087 to the 20th power. And I showed you what this should look like in the calculator on the right here. And so this is going to give us $5,303.85. So how much interest was earned over the 20 years? We take this amount, $5,303.85, subtract out our 1,000, and that tells us that $4,303.85 was our interest. Okay, again, our interest is equal to our future value minus the principal. I would like you to do this for C and D. We're finding the future value now for 40 years. And then D says how much interest was earned over those years. Okay, so for 40 years, we have A is equal to 1,000, 1 plus 0.087, and now our exponent is 40. This gives us $28,130.78. So how much interest was earned over those 40 years? We take our $28,130.78 minus 1,000, which gives us $27,130.78. Then it says how much interest was earned just the last 20 years. So for the last 20, we have to take our interest over the 40, $27,130.78, and subtract out the first 20, the $4,303.85, and that leaves us with $22,826.93. Compare the amount of interest earned in the first 20 years to the amount in the last 20 years. So the first 20, it was our $4,303.85. The last 20 was the $22,826.93. So if we subtract these, we get that it was $18,523.08 more the last 20 years. Okay, so compound interest. This is paid more than once a year. So in our previous example, the interest was computed and added to the account every year. Some accounts compound the interest more frequently. So compounding annually, this is where n equals 1, n is the number of times per year. So this is compounded every 12 months. Semi-annually, n equals 2, so that's every 6 months. Quarterly, n equals 4, so this happens every 3 months. Monthly, n equals 12, so this happens once a month. Weekly, n equals 52. So the length of each compounding period, this is now 12 over 52. And then our daily compounding, n equals 365, unless it says that we're using that banker's rule, which is 360. Then our compounding period, we either use 12 over 365 or 12 over 360. Okay, so it says, remember the interest rate that is reported is for the year. So if the money is being compounded more than once per year, we split the percentage equally for each of the compounding periods. So an account earns 12% interest and is compounded quarterly. What is the quarterly interest rate? So here, our 12% interest, R is 0.12. Compounded quarterly means n equals 4. So the quarterly interest rate, we would have R divided by n. So this is 0.12 divided by 4, which is 0.03 or 3%. How many times will interest be compounded in 10 years' time? So here our t is 10, our n is still 4 from above. So we do n times t. This is 4 times 10, which is 40 times. Now we did these two quantities because this goes to our next formula. This is the amount in account for compounding interest paid n times per year. A equals P times 1 plus R over n raised to the nt power. All right, and everything stands for the same as we had described before. So our P is our principal, A is the future value, R is the rate, R over N is the fraction of the rate, T is the years, N is the compounding periods per year, and N times T is the total number of compounding periods. So this says, what is the future value of $1,500 if it is deposited into an account that earns 5.4% compounded quarterly for 20 years, and then 40 years, and then compare the interest earned in the first 20 to the interest earned into the next 20. So let's do the first 20 years. So our P is 1,500. Our R value is 0.054, and it's for the next 20 years. So T equals 20. So we have A equals 1,500 times 1 plus 0.054 over 4 raised to the 4 times 20 power. And you can see I provided here what this looks like in the calculator. So our future value is going to give us $4,385.22. So to find our interest, we take the $4,385.22 minus the $1,500, and this gives us $2,885.22. And again, this represents the first 20. Okay, I want you to calculate the amount of interest that we get after 40 years. So first find the future value and then the interest for 40 years. Okay, so we have our A is equal to 1,500. We do 1 plus 0.054 divided by 4 times 4 times 40. So our future value, this is going to give us $12,820.11. So our interest, we take that $12,820.11 minus the $1,500 that we deposited, and that leaves us with $11,320.11. So this was for 40 years. Okay, so if we want to get the last 20, years interest, we're going to take our $11,320.11 minus the first 20, the $2,885.22, and that leaves us with $8,434.89. Okay, so that's our first 20 on the left. This is our last 20 on the right. So if we want to compare them, we can subtract. So here we have $8,434.89 minus the $2,885.22, and that leaves us with $5,549.67 more in the last 20 years. Okay, continuous compounding. What happens as you have more and more compounding periods per year. Let's take a look at the formula. When P is 1, R is 1, and T is 1, and see what happens as we let n get bigger. So if you look at the table here, you can see there appears to be a limiting value of, this is 2.7183. You can see that happening here. The actual value is a decimal that never terminates and never repeats. So we give this irrational number a symbol, and that's our E. So continuous compounding, this is the compounding periods increase infinitely. So down to a trillionth of a second, quadrillionth of a second, etc. So calculating the amount in an account for continuous compounding, this is our formula. A equals P times E raised to the RT power. And a special note here, make sure that you use the E key on your calculator. So this is second, and then you hit the natural log or ln button on your calculator to get the E key. So here's our example of continuous compounding. So I would like you to try this one. If a loan for $2,000 is taken out at a rate of 4.3% for 5 years and the interest is compounded continuously, how much will need to be repaid at the end of 5 years? Please do this one. Okay, our P is 2,000, our R is 0.043, and our T is 5. So it's compounded continuously. We're going to use our new formula with the E. So A is equal to 2,000 times E raised to the 0.043 times 5 power. And you should get $2,479.72. Okay, to calculate present value, we've used the same formulas for compound interest to determine the future value of a present amount. We can also use them to determine the present amount needed to accrue a certain future value. So what we're basically doing is if we take our formula to solve for P, we're going to divide by this whole term. So P is equal to A divided by 1 plus R over N raised to the N times T power. To do the same thing for continuous compounding, we're going to divide by our E raised to the RT. So P is equal to A divided by E raised to the RT power. And as a note, when computing P, you always round up. So think P is up, P is up, to make sure that the future value is enough. So it says how much needs to be invested today so that 40 years from now, there is $50,000 in the account. Assume the account earns 8.9% compounded monthly. So here, your T is 40, 50,000, this is our A, our future value. Our R is 0.089, and compounded monthly means N equals 12. So our P is equal to 50,000 divided by 1 plus 0.089 divided by 12. 12 times 40 is our exponent. And this comes out to be $1,440. And if you notice, I gave you the calculator snapshot here. And we have, if I look at my decimal here, we have this 4 afterwards. So it's more than a 0. So we have to round this up to 75 cents. So again, if you have anything that's more than 0, then you round up. So here is an example. If you were to use 74 and not round up here, the future value A is equal to this $49,999.86 about. So that's not enough. we're a few cents short. If we are looking at, if we plug in 75 cents, then we see our A comes out to be 50,020 cents, which is enough here. Okay? B says, assume the account earns 8.9% compounded continuously. So we have to do the calculations here and find the future value. So 8.9%, this is our R equals 0.089. Compounded continuously means we're going to use our formula with E. So T is 40 still, our A is 50,000 still. So P is equal to 50,000 divided by E to the 0.089 times 40. And this comes out to give you $1,421, and then it's 0.941236. So we have a 1 here, which is more than 0, which means we have to round up. And so our amount will be $1,421.95. If we'd figure out our future values, if I plug in 94 cents, we have A is equal to $1,421.94 times E to the 0.089 times 40. This comes out to give us $49,999.96. Whereas if we round up to the 95 cents, this is 1421.94 E to the 0.089 times 40 cents. So this comes out to give us 50,031 cents. Again, we want to make sure that we always have enough for our future value, so you always round up. How much money should be deposited today in an account that earns 7% interest compounded weekly so that it will accumulate to $10,000 in 8 years? I want you to try this one, please. Okay, so 7% interest, R equals 0.07. Weekly, N equals 52. Our future value is 10,000 and 8 years is our time. So P is equal to 10,000 divided by 1 plus 0.07 divided by 52 raised to the 52 times 8 power. And this comes out to give you $5,714.25. Okay, understanding and computing effective annual yield. So effective annual yield, effective rate, or simple interest rate. This is a simple interest rate that produces the same amount of money in an account at the end of 1 year as when the account is subject to compound interest rates. So when borrowing money, this is usually called the annual percentage rate, or APR. So the nominal rate is the stated rate. And so let's work this out. You deposit $1 into an account that earns 6% interest compounded daily. Using 360 days, we're going to use the banker's rule. Find the future value after 1 year. So our P is 1. 6%, R is 0.06. Compounded daily, we said we're going to say N equals 360. And our T is 1. So A is equal to 1 times 1 plus 0.06 over 360 times 360, raised to the 360 times 1 power. And this comes out to give you 1.06, or $1.06. So what simple interest rate would get you the same future value? So we can use our simple interest rate, A equals P times 1 plus RT to find this. So we have $1.06 equals 1 times 1 plus R times 1. That gives us 1.06 equals 1 plus R. I subtract the 1 and R equals 0.06, so 6%. Now in this case it was the same, but that will not always be the case. Okay, so let's look at this next one. Here's our formula for computing effective annual yield. Y is the decimal form of the effective annual yield. R is the nominal interest rate in decimal form. N is the number of compounding periods per year. So a couple takes out a loan for a house for 5% compounded daily using 360. When they go to sign the paperwork, it says the annual percentage rate is 5.13%. Why? So let's calculate this. 5%, this is our R, 0.05. N equals 360. And we need to plug this into our effective annual yield formula. So Y is equal to 1 plus 0.05 divided by 360 raised to the 360 times 1 essentially. That's why we're just doing the 360 minus 1. And you can see I gave you what this looks like in the calculator here. This comes out to be 0.05. And notice they said it's 5.13. So we have 0.1267. If I cut it here, the 6 rounds that 2 up, and it's 0.0513, which is 5.13%. So again, this is the simple interest rate. And it earns the same amount in 1 year as money invested at 5% compounded daily. And that is all I have for you for today.